A beam of light racing from Earth takes over 4 years to reach even our closest stellar neighbor. At that speed, crossing our galaxy takes 100,000 years. We are trapped in a cosmic prison, locked behind bars made of physics itself. But what if those bars just bent? Scientists have cracked a method that could send spacecraft 10 times faster than light, turning century-long voyages into decade-long adventures. You'll discover warp bubbles appearing in laboratories, gravitational waves hiding alien footprints, and energy requirements dropping from impossible to just barely insane. If you're ready to see this breakthrough, hit that like button and subscribe, because we're about to rewrite reality. Let's begin. Our fastest spacecraft ever built, the Parker Solar Probe, screams through space at 190,000 miles per hour. Sounds impressive until you realize it would still take 70,000 years to reach the nearest star. That trip would begin during the last ice age and end in our distant future. Humanity is stuck in a speed trap we cannot escape with rockets alone. Light itself moves at 670 million miles per hour, and even that takes 4.5 years to bridge the gap between us and Proxima Centauri. The galaxy measures 100,000 light-years across. Do the math, and crossing it becomes a journey spanning millennia. Every star you see twinkling in the night sky represents a destination that current technology renders completely unreachable within a human lifetime. The Voyager probes, launched in 1977, are now barely 14 billion miles from home. They have been traveling for nearly 5 decades. Yet they have not even left our solar system's gravitational influence completely. The stars remain impossibly distant. We are cosmic infants, crawling when we need to sprint. Here is the brutal truth. Space is not just big, it actively mocks our ambitions. The distances between stars are so vast that even traveling at 99% of light speed would turn interstellar missions into generational commitments. Your great-great-grandchildren might see the destination you aimed for. Every propulsion system we have built operates on the same basic principle. Throw stuff out the back to push forward. Chemical rockets burn fuel. Ion drives shoot electrified particles. Nuclear engines blast heated gas. All of them obey classical physics, and all of them crawl compared to the cosmic highway we need to cross. Scientists call this the tyranny of the rocket equation. The more fuel you carry, the heavier your ship becomes. The heavier your ship, the more fuel you need. It becomes a nightmare spiral where your fuel tanks end up larger than entire cities just to reach a fraction of light speed. Adding more thrust only adds more weight. We have sent robots to Mars, landed rovers on distant moons, and photographed the edge of our observable universe. Yet we remain trapped in our own backyard, staring at fences we cannot climb. The nearest potentially habitable planet sits 4 light-years away. With current technology, getting there would require 25,000 years of continuous flight. Something has to change. The cosmos is filled with billions of potentially habitable worlds, yet we can barely reach the closest rock in our own neighborhood. But what keeps us chained to this painfully slow reality? The answer lies in one man's equations, written over a century ago. Albert Einstein published his theory of special relativity in 1905, and with it, he built an invisible prison around humanity. His equations revealed something shocking. Nothing with mass can reach or exceed the speed of light, ever. The universe itself enforces this rule through the fabric of space and time. The reason sounds deceptively simple. As objects accelerate closer to light speed, they gain mass. Not just a little bit. The faster you go, the heavier you become, exponentially. A spacecraft approaching light speed would weigh more than entire galaxies. Moving it even 1 mile per hour faster would require astronomical energy increases. This creates a cosmic catch-22. You need energy to accelerate mass, but accelerating makes that mass increase, which requires more energy, which increases mass further. The cycle spirals into infinity right at the moment you would cross the light speed threshold. The universe essentially says, you can get close, but you can never touch this limit. Einstein called it a universal speed limit, and for over 100 years, his math has held firm against every challenge. Particle accelerators smash atoms together at 99.99% of light speed, and they confirm his predictions with terrifying accuracy. Objects really do get heavier. Time really does slow down. The rules are absolute. Scientists have tried everything to find loopholes. They experimented with exotic propulsion methods. They calculated trajectories using gravitational assists. They proposed generation ships, where entire civilizations would be born, live, and die during the journey. None of it changes the fundamental problem. Einstein's equations lock the door, and conventional physics cannot find the key. Physicists call these laws inviolable. Break them, and you break causality itself. You create paradoxes where effects happen before causes. You tear apart the logical structure that holds reality together. The universe would rather collapse than let something with mass go faster than light. Time dilation makes things worse. Even if you somehow reached 99% of light speed, time would flow differently for you than for everyone back home. A journey that feels like 10 years to you might span decades or centuries on Earth. You would return to find everyone you knew long dead, their great-grandchildren now elderly. The isolation is complete. Length contraction adds another twisted layer. At extreme speeds, space itself appears to compress in front of you. Distances shrink. A trip that should take years might feel like months to you while decades pass outside. The universe warps around fast-moving objects in ways that defy common sense. For generations, physicists accepted this as the final word. Light speed is the speed limit. Nothing escapes it. Teaching this became fundamental to every physics curriculum on Earth. Breaking it seemed as impossible as creating a square circle or making 2 + 2 = 5. But some scientists refused to accept permanent defeat. They started asking a different question. What if we are thinking about movement all wrong? Accelerating even a small spacecraft to light speed requires more energy than currently exists in every fuel tank, battery, and power plant on Earth combined. Then multiply that by 1 billion. You still fall short. The mathematics behind this nightmare are confirmed and ironclad. As velocity increases, so does kinetic energy. Near light speed, energy requirements do not just grow, they explode. A spacecraft weighing just 1 ton would need approximately 9 × 10⁻16 joules to reach light speed. That equals the total annual energy output of human civilization, all consumed in seconds, just to move a small vehicle. Nuclear fusion, the same process powering stars, offers our most energy-dense fuel source. Yet even converting the entire mass of a large asteroid into pure energy would barely budge a decent-sized starship to a meaningful fraction of light speed. We are not talking about difficult engineering problems. We are talking about fundamental impossibilities. Project Daedalus, designed in the 1970s, proposed using fusion rockets to reach 12% of light speed. Sounds modest until you see the design. A ship mostly composed of fuel tanks the size of skyscrapers, carrying 50,000 tons of deuterium and helium-3. The payload compartment carrying actual cargo and crew would be tiny by comparison, and that massive ship would still take 2 decades to reach just the outer edges of our neighboring star systems. Antimatter engines could theoretically improve this ratio. When matter meets antimatter, they annihilate completely, converting 100% of their mass into energy. It represents the most efficient fuel theoretically possible. The problem? We can only produce antimatter 1 particle at a time using massive accelerators, and storing it requires magnetic bottles that consume enormous power. Producing enough antimatter to fuel 1 interstellar mission would take thousands of years with current technology. Some physicists proposed solar sails, giant reflective sheets pushed by light pressure from stars. These require no fuel at all, just patience. The acceleration is glacial, measured in fractions of inches per second, compounding over years. Reaching even 10% of light speed would take decades of continuous acceleration, and the sail would need to be miles across, impossibly thin, yet strong enough to not tear apart. Every conventional propulsion method hits the same wall. The faster you want to go, the more fuel you need. The more fuel you carry, the heavier your ship becomes. The heavier your ship, the more energy you need to accelerate it. Engineers call this diminishing returns. Poets might call it cosmic mockery. Chemical rockets tap out at around 5 miles per second. Ion drives might reach 20 or 30. Nuclear thermal engines could potentially hit 50. Even the most optimistic fusion designs cap around 3,000 miles per second, still just 1% of light speed. We are throwing pebbles at a mountain, hoping to move it. The energy trap is not just about building bigger engines or finding better fuel. It represents a fundamental barrier written into the structure of reality itself. Einstein's equations ensure that reaching light speed with any massive object demands infinite energy. Infinite means impossible. No clever engineering, no breakthrough technology, no amount of determination changes that equation. Yet the trap only exists if you play by the old rules. What if movement itself is not what we think it is? Earth might be dying, and we have nowhere else to go. That cold fact keeps researchers awake at night, because looking around our cosmic neighborhood reveals a grim truth. Every other planet in our solar system is a hostile wasteland. Mars, the closest candidate, is a frozen desert with temperatures dropping to minus 225 degrees Fahrenheit. Its atmosphere is 96% carbon dioxide, and so thin that standing on the surface equals being 19 miles high in Earth's atmosphere. Your blood would literally boil in the low pressure. Dust storms cover the entire planet for months, and radiation from space blasts the surface constantly because Mars lost its protective magnetic field billions of years ago. Venus looks even worse. Beneath its thick clouds, the surface temperature reaches 860 degrees Fahrenheit, hot enough to melt lead. Atmospheric pressure there equals being 3,000 feet underwater on Earth. The atmosphere itself is mostly carbon dioxide mixed with clouds of sulfuric acid. Probes sent to Venus have survived less than 2 hours before being crushed and melted. Living there is not difficult. It is impossible. The gas giants offer no surface to stand on at all. Jupiter, Saturn, Uranus, and Neptune are essentially enormous balls of hydrogen and helium, with crushing pressures and winds reaching 1,000 miles per hour. Their moons present slightly better options but remain frozen, airless, and lethal. Titan, Saturn's largest moon, has liquid methane lakes and a thick atmosphere. Sounds promising until you realize the surface temperature sits at minus 290 degrees Fahrenheit. You would freeze solid in seconds without protection. Europa, orbiting Jupiter, might harbor liquid water beneath miles of ice, but accessing it would require drilling through a frozen shell in one of the most radiation-saturated environments in the solar system. Mercury swings between 800 degrees on its sunny side and minus 300 degrees in shadow. The Moon has no atmosphere, no water, and faces the same radiation bombardment as Earth, but without any protective magnetic field. Every single body in our solar system is either too hot, too cold, too toxic, or completely lacking the basic requirements for human life. Terraforming these worlds remains pure speculation. Even the most optimistic estimates suggest making Mars barely habitable would take thousands of years and require technology we have not invented yet. We would need to thicken its atmosphere, warm its surface, restart its magnetic field, and create breathable air. Each step presents nearly insurmountable challenges. Earth is not just our home, it is our only viable home for potentially millions of years into the future, even with unlimited technology. That means if climate change, asteroid impacts, or any other catastrophe makes Earth uninhabitable, humanity has no backup plan. We need to reach beyond our solar system, not just for exploration, but for survival. The problem? Those potentially habitable worlds exist light years away. Proxima Centauri b orbits in its star's habitable zone just 4 light-years distant. The TRAPPIST-1 system contains 7 Earth-sized planets, 3 potentially habitable, 39 light-years away. Kepler 452b closely resembles Earth and sits 1,400 light-years distant. These worlds represent our future homes, but they might as well exist in another dimension with current technology. This is why faster-than-light travel is not a luxury. It is an evolutionary necessity. We need new worlds, and reaching them demands breaking the most fundamental speed limit in physics. Telescopes have identified over 5,000 confirmed planets orbiting distant stars, and dozens sit in the habitable zone where liquid water could exist. We can see them. We can measure their size, composition, and orbital distance. We can calculate their surface temperatures and atmospheric makeup. We just cannot reach them. Proxima Centauri b haunts astronomers because it represents everything we want and cannot have. Just 4.2 light-years away, this planet orbits a red dwarf star in the habitable zone. It might have oceans. It could harbor life. Early data suggests it might even have a magnetic field protecting it from radiation. Scientists estimate it receives similar energy levels as Earth does from our star. The TRAPPIST-1 system, discovered in 2017, sparked even more excitement. 7 Earth-sized planets orbit a small, cool star just 39 light-years away. 3 of those planets sit squarely in the habitable zone. Computer models suggest they could have atmospheres, weather systems, and stable climates. Liquid water is not just possible but likely. Kepler 452b, nicknamed Earth's cousin, orbits a star remarkably similar to our own. It receives only 10% more energy than Earth gets, suggesting surface temperatures in the right range for life. It sits 1,400 light-years distant, and discovering it felt like finding a twin sibling across an uncrossable ocean. These discoveries keep multiplying. Every year brings dozens of new candidates. Planets with thick atmospheres, worlds with day-night cycles similar to Earth, rocky planets with just the right mass to hold onto their air without crushing anything on the surface. We have found frozen worlds, lava worlds, ocean worlds, and desert worlds. The galaxy teems with possibilities. Yet every single one remains completely unreachable. Even Proxima Centauri b, our closest candidate, requires 40,000 years to reach with current spacecraft speeds. TRAPPIST-1 would take 600,000 years. Kepler 452b demands 25 million years of continuous flight. These numbers stop being travel times and start becoming geological epochs. We are trapped behind a window, watching paradise we cannot enter. Astronomers can tell you the atmospheric composition of planets dozens of light years away, but we cannot send even a small probe to investigate them in anything resembling a reasonable time frame. The James Webb Space Telescope can photograph the chemical signatures of water vapor and oxygen in alien atmospheres. Yet physically visiting those worlds remains pure fantasy. The frustration goes beyond scientific curiosity. These planets represent potential homes for future generations. They could be refuges if Earth becomes uninhabitable. They might harbor ecosystems we could study, resources we could use, or even intelligent civilizations we could contact. Everything we want to know, everything we need to reach, sits just beyond our grasp, behind an insurmountable wall of distance and physics. Radio signals traveling at light speed would take years to reach these worlds. Even if we detected intelligent life today and sent a message, their reply would not arrive until decades later. A conversation would span generations. Physical travel seems impossible without a complete reimagining of how movement works. Unless we stop trying to move through space and start moving space itself. Miguel Alcubierre was a graduate student obsessed with Star Trek when he decided to actually calculate whether warpdrive could work in real physics. In 1994, he published a paper that made professional physicists do double takes because his math was not just creative, it was technically correct. The Alcubierre drive concept does not accelerate a spacecraft through space at all. Instead, it creates a bubble around the ship that warps space itself. Space contracts in front of the vessel and expands behind it, creating a wave that carries the bubble forward. The ship inside remains stationary relative to the space immediately around it, experiencing no acceleration forces whatsoever. Think of it like a surfer riding a wave. The surfer is not swimming through the water or creating their own speed. They are being carried by the wave itself, standing still on their board while the ocean does all the work. Alcubierre's equations described a spacecraft riding a wave through space-time in exactly the same way. The brilliance comes from exploiting a loophole in Einstein's equations. Relativity says nothing with mass can move through space faster than light. Fine. But Einstein never said space itself cannot move faster than light. In fact, cosmologists know space expands faster than light at the edges of the observable universe. That expansion is how the universe grew from a tiny point to its current size in just under 14 billion years. If space can already break the speed limit, why not harness that property? Alcubierre's equations showed you could theoretically create negative energy density in front of a ship, causing space to contract there, while positive energy behind causes expansion. The bubble containing the ship gets propelled forward by this asymmetric spacetime distortion. No thrust needed, no acceleration felt. The ship simply rides the wave. His paper sent shockwaves through theoretical physics. For the first time, someone had described a faster-than-light travel mechanism using accepted general relativity equations. It was not speculative science fiction. It was peer-reviewed mathematics, published in a legitimate physics journal. The method appeared technically legal, according to the known laws of physics. Other scientists rushed to verify his calculations. They found the math held up. Space-time could theoretically be warped in this way without violating causality or breaking relativity. The energy requirements? Absolutely astronomical, but technically finite. That represented a massive improvement over conventional propulsion, which requires literally infinite energy to reach light speed. The Alcubierre drive could theoretically reach any speed, 10 times light speed, 100 times, 1,000 times. The bubble is not moving through space, so relativistic effects like time dilation and length contraction do not apply. Crew members inside would experience normal time flow. They would not age slower than people back home. They would not see distances compress. Physics inside the bubble remains completely normal. Alcubierre himself admitted he never expected the concept to work mathematically. He was just a physics student, playing with equations inspired by his favorite television show. Yet his recreational calculation accidentally revealed a genuine possibility hidden in the structure of space-time itself. Reality appeared to have a cheat code embedded in its operating system. Of course, actually building one presented complications that made the theory look almost easy by comparison. But the door was open. The impossible suddenly looked merely extremely difficult. Space-time is not empty nothingness. It is an actual thing, a fabric that can bend, stretch, twist, and ripple. Every massive object creates a dent in this fabric, like bowling balls sitting on a stretched sheet. That dent is what we experience as gravity. Einstein described this over a century ago, and we have confirmed it countless times. GPS satellites must account for time flowing slightly faster in orbit than on Earth's surface because they sit higher in the gravitational well. Experiments with atomic clocks on airplanes show the same effect. Black holes warp spacetime so severely that nothing can escape once you cross the event horizon. The Alcubierre drive takes this concept and weaponizes it. Instead of letting gravity naturally warp space, you artificially create a bubble of warped space around your spacecraft. The warp contracts space in front of you and expands it behind you, generating a wave that pushes the bubble forward. Your ship never moves through space. Space moves around the ship. It sounds like semantics, until you realize this sidesteps Einstein's speed limit completely. Relativity restricts movement through space, but places no limits on how fast space itself can move. The distinction matters because all those nightmare side effects of near light speed travel, time dilation, length contraction, infinite energy requirements, all disappear when you are not actually moving. Inside the warp bubble, physics operates normally. You can walk around the ship, drink coffee, play cards, and experience time flowing at exactly the same rate as people back on Earth. No twin paradox where you return younger than your siblings. No relativistic effects smearing your vision. The bubble isolates you from the extreme space-time distortions happening at its edges. The wave itself could move at any speed. Alcubierre's original calculations suggested 10 times the speed of light would be relatively easy. More recent variations have proposed speeds reaching 100 or even 1,000 times faster. At those velocities, Proxima Centauri becomes a 2-week trip. The entire Milky Way galaxy becomes crossable in a human lifetime. The warp bubble would appear strange to outside observers. Light cannot normally escape from the region of highly compressed space in front of the ship, making it partially invisible. The expanding space behind would redshift light to radio wavelengths. The bubble might emit exotic radiation as it moved, creating a visible wake through space-time itself. From inside, you would see space compressed ahead of you, making distant destinations appear closer than they actually are. Stars would shift color as their light gets distorted by the warp field. Looking backward, space would appear to stretch away into infinity, though you would still see your starting point just at shifted wavelengths. The mathematics describing this get complex quickly, involving tensor equations and differential geometry, but the core concept remains beautifully simple. Surf space-time like an ocean wave, letting the universe do the work while you sit comfortably inside a bubble of normal reality. The key lies in creating asymmetric space-time curvature. That requires manipulating the energy density of space itself in ways that seem almost magical, which brings us to the biggest problem with the entire concept. Alcubierre's warpdrive requires something that probably does not exist: exotic matter with negative mass and negative energy density. This is not antimatter, which annihilates regular matter in bursts of energy. This is something far stranger that repels instead of attracts, pushes instead of pulls, and makes gravity work backward. Normal matter curves space-time inward, creating the gravitational wells that hold planets in orbit and make apples fall from trees. Exotic matter would curve space-time outward, creating a gravitational hill that pushes things away. It represents the opposite of everything we know about how mass and energy behave in our universe. Does negative mass exist? We have never observed it directly. No one has ever measured it, created it, or found evidence of it occurring naturally anywhere in the cosmos. It remains entirely theoretical, a mathematical possibility that the equations of general relativity permit, but nature has apparently never bothered to manifest. The amount needed for a warp drive makes things worse. Alcubierre's original calculations suggested you would need negative mass equivalent to the total mass energy of Jupiter just to warp space around a small spacecraft. Jupiter weighs 300 times more than Earth. Converting that much normal matter into exotic matter, even if possible, would require energy expenditures dwarfing anything humanity could generate. Critics pounced on this requirement immediately. Sure, the math works, they said. The equations are valid, but demanding materials that do not exist makes the whole concept useless. You might as well design a perpetual motion machine that runs on unicorn tears. The physics checks out, but the ingredients are fantasy. Some researchers tried to find alternatives. Could you use intense electromagnetic fields to create negative energy density in vacuum? Maybe quantum fluctuations could be manipulated to generate the required effect. Dark energy, the mysterious force accelerating the universe's expansion, exhibits some properties similar to negative pressure. Could we somehow harness or concentrate it? These questions generated decades of theoretical papers, but no practical answers. Creating sustained regions of negative energy density appeared to violate several fundamental principles, including quantum field theory's energy conditions. The universe seems to have built-in protections, preventing large-scale negative energy concentrations, probably to avoid causality violations and other reality-breaking paradoxes. The Casimir effect offered a tiny glimmer of hope. When you place two uncharged metal plates extremely close together in vacuum, quantum fluctuations between them create less energy density than in the surrounding space. That technically counts as negative relative energy density, though the absolute value remains positive. The effect is measurable, confirmed, and absolutely real. Could this principle be scaled up? If you could create and manipulate Casimir-like effects on large scales, you might generate the space-time distortions needed for a warp bubble without requiring exotic matter at all. The energy would still need to come from somewhere, but at least you would be working with known physics rather than theoretical ghosts. This is where Harold White enters the story, and where everything changes from pure theory to something approaching experimental physics. Dr. Harold White spent years researching propulsion physics at NASA's Johnson Space Center in Houston. His team operated a lab dedicated to investigating exotic propulsion concepts, the kind of fringe science that makes colleagues raise eyebrows but occasionally produces breakthrough discoveries. In 2011, White published new calculations suggesting the energy requirements for an Alcubierre drive might be dramatically lower than originally thought. His revised math showed that optimizing the shape of the warp bubble could reduce energy needs by several orders of magnitude. Instead of requiring Jupiter mass amounts of exotic matter, you might only need several hundred kilograms. Still exotic, still unavailable, but suddenly the concept shifted from physically impossible to merely incredibly difficult. Then, in 2021, something unexpected happened. White's team was studying the Casimir effect using specialized equipment designed to measure nanoscale forces between metal plates. They were not trying to create a warp bubble. They were investigating whether Casimir forces could be useful for spacecraft attitude control. Basic research, nothing revolutionary. During one experimental run, their sensors detected something bizarre, a measurable warp in spacetime at the nanometer scale. The readings matched theoretical predictions for what a tiny warp bubble would look like. They had accidentally created the exact space-time geometry that Alcubierre described, just at a scale millions of times smaller than needed for actual propulsion. White's team repeated the experiment multiple times. The effect remained consistent and measurable. They were not seeing instrument errors or quantum noise. They were observing actual, repeatable, space-time distortion created by manipulating the Casimir effect. A warp bubble, microscopic but real, had appeared in a laboratory on Earth. The implications detonated through the propulsion physics community. Warp-drive geometry was not just theoretical anymore. It could be created, measured, and studied experimentally. If you could make a nanoscale warp bubble, then scaling it up became an engineering challenge rather than a physics impossibility. Critics demanded verification. Other labs needed to reproduce the results before anyone could claim definitive proof. The equipment required is specialized and expensive, so independent confirmation takes time. Some physicists suggested alternative explanations for White's readings. Maybe electromagnetic interference. Maybe quantum effects being misinterpreted. Skepticism remains healthy in science. Yet White's team had calibrated their instruments carefully, accounted for known sources of error, and documented everything meticulously. The data looked solid. More importantly, the effect appeared when theory predicted it should, and vanished when conditions changed. That kind of correlation suggests real phenomena rather than measurement artifacts. NASA quietly increased funding for White's lab. Other government agencies took notice. Private aerospace companies started hiring propulsion physicists to investigate warp field generation. The race was on, not to build a warp drive immediately, but to understand whether scaling up from nano to macro was achievable. The exotic matter problem still loomed large. Even at reduced energy requirements, you still needed negative energy density to create asymmetric space-time curvature. White's experiments showed Casimir effects could produce warp-like geometry, but only at tiny scales with tiny amounts of energy manipulation. Going from nanometers to meters represented a billion-fold increase in scale. Still, the psychological barrier had shattered. Warp bubbles existed in reality, not just on paper. That changed everything. Suddenly, other research teams started dusting off old warpdrive papers and looking for overlooked details. Maybe the answer was hiding in plain sight all along. The Casimir effect sounds like magic, but emerges from one of the weirdest confirmed facts about reality. Empty space is not empty. Quantum field theory says vacuum constantly churns with virtual particles popping into and out of existence. These particles exist for infinitesimally brief moments, borrowing energy from quantum uncertainty, then disappearing before the universe notices the debt. You cannot see these virtual particles directly, but you can detect their effects. They create a faint background energy that permeates all of space. Normally, this quantum vacuum energy is uniform, pushing equally in all directions, so you never notice it. But in 1948, Dutch physicist Hendrik Casimir predicted something strange would happen if you placed two uncharged metal plates very close together. The metal plates would restrict which virtual particles could exist in the gap between them. Only particles with wavelengths smaller than the gap could appear there. Outside the plates, all wavelengths of virtual particles could exist freely. This creates an imbalance, more quantum pressure, pushing the plates together from outside than pushing them apart from inside. The result? The plates attract each other with measurable force, despite having no electric charge and no conventional interaction. They are being pushed together by an imbalance in quantum vacuum fluctuations. This force is tiny, only noticeable when plates are separated by distances smaller than a human hair. But it is absolutely real and has been measured countless times. The Casimir effect proves negative energy density can exist in nature. The space between those plates has less quantum vacuum energy than normal empty space. That technically counts as negative energy relative to the surrounding vacuum. This is crucial because it suggests exotic matter might not be required for warp drives if you could amplify and control Casimir-like effects. White's experiments exploited this principle. By carefully arranging capacitor plates in specific geometries, his team created regions where quantum vacuum energy differed from baseline. Those differences in energy density warped spacetime slightly, creating measurable distortions. The warp was microscopic, but it was there. Scaling this up presents enormous challenges. The Casimir force drops off rapidly with distance. Move the plates even slightly farther apart, and the effect vanishes. Creating Casimir-like negative energy densities across distances measured in meters rather than nanometers would require completely new techniques, possibly involving exotic materials or quantum technologies that do not exist yet. Some physicists proposed using metamaterials, artificially structured materials that bend light and electromagnetic fields in unusual ways. Others suggested quantum computing techniques might allow precise control over vacuum fluctuations. A few radical thinkers wondered if dark energy, the mysterious force accelerating the universe's expansion, could be related to manipulable vacuum energy states. The energy requirements remained staggering, even with Casimir effects reducing them. You still need to create and maintain sharp energy gradients across the warp bubble boundary. That demands power sources far beyond anything currently available. Nuclear fusion might provide enough concentrated energy, but controlling it precisely enough to shape space-time represents an entirely different challenge. Yet, the door was open. Exotic matter might not be necessary after all. Real, measurable physics could potentially create warp-like space-time distortions. The path from nanoscale demonstration to spacecraft-scale application looked long and uncertain, but it existed. That represented genuine progress, not just theoretical speculation. The next breakthrough would come from an unexpected direction, listening to the universe itself for signs that someone else might have already solved the problem. When Alcubierre first calculated the energy requirements for his warp drive, the numbers were apocalyptic. You would need to convert the entire mass of Jupiter into pure energy and somehow concentrate it into exotic matter. That equals about 2 times 10 to the 30 kilograms, or roughly 1.9 times 10 to the 47 joules of energy. For perspective, the most powerful nuclear bomb ever detonated released about 2.1 times 10 to the 17th joules. You would need that bomb's energy output multiplied by 1 trillion times. Those numbers killed serious interest immediately. Sure, the math was elegant and the concept legal according to relativity, but requiring more energy than multiple star cores made the whole concept a theoretical curiosity. Building it seemed as realistic as constructing a ladder to the moon. But Harold White noticed something in the equations. The energy requirements depended heavily on 2 factors: the thickness of the warp bubble wall and the overall shape of the bubble geometry. Alcubierre's original model used relatively thick walls and a simple spherical shape because that made the math cleaner. What if you optimize those parameters? White proposed reshaping the bubble into a toroidal configuration, like a donut rather than a sphere. He calculated that making the bubble wall oscillate in thickness rather than remaining static could dramatically reduce energy needs. The math got significantly more complex, but computers could handle it. When he ran the optimized numbers, the results shocked everyone. Energy requirements dropped from Jupiter mass to something closer to 500 kilograms of exotic matter equivalent. Still enormous, still exotic, but several orders of magnitude more reasonable than before. That mass equals about a small satellite. You could theoretically fit it inside a spacecraft rather than needing a planet-sized energy source. Further refinements continued improving the outlook. Different research groups proposed various bubble geometries, elongated ellipsoids, figure-8 configurations, nested shells with different densities. Each optimization chipped away at the energy requirements. Some recent papers suggest you might only need several dozen kilograms of negative energy density if you get the geometry precisely right. These improvements happened purely through mathematical optimization, finding more efficient ways to warp spacetime that achieve the same propulsive effect with less energy input. It mirrors how engineers improved rocket efficiency over decades by refining nozzle shapes, fuel mixture ratios, and combustion chamber designs. The fundamental physics remained the same, but clever optimization extracted better performance. The really exciting development came when researchers realized you might not need sustained exotic matter at all. Some models suggest you could use ordinary energy to create temporary regions of negative energy density through quantum effects, maintaining them just long enough to generate thrust, then letting them collapse and recreating them. Think of it like internal combustion engines that burn fuel in pulses rather than continuous combustion. This pulsed warp drive concept could theoretically run on advanced fusion reactors or antimatter annihilation without requiring exotic matter storage. You would need exotic effects, but only transiently and in controlled ways. That shifts the challenge from materials science to precision engineering. Could these optimization really work? The mathematics appears sound, confirmed by multiple independent physicists. But math only tells you what might be possible according to known laws. Whether reality cooperates with these theoretical models remains unproven until someone builds working hardware. Still, dropping energy requirements from Jupiter mass to satellite mass represents genuine progress. It moved warp drives from impossible to merely extraordinarily difficult. Sometimes that distinction makes all the difference. And other research teams were approaching the problem from an entirely different angle. Brazilian physicist José Natario looked at Alcubierre's equations and saw room for improvement. In 2002, he published an alternative warp drive model using different geometric tricks to achieve similar results. The Natario drive, as it became known, creates spacetime distortions through a modified tensor field configuration that some physicists argue is more stable than Alcubierre's original design. The key difference lies in how the warp bubble interfaces with normal spacetime. Alcubierre's model creates sharp discontinuities at the bubble boundary where space abruptly transitions from compressed to normal to expanded states. Those sharp boundaries require intense energy concentrations and might generate problematic radiation or gravitational effects. Notario smoothed out those transitions. His model distributes the spacetime distortion more gradually across a larger volume, reducing the peak energy densities required at any single point. Think of it like the difference between a sharp cliff edge and a gentle slope. Both change elevation, but the slope is more stable and requires less dramatic engineering to traverse. This geometric revision carries important implications for theoretical stability. Sharp energy boundaries in Alcubierre's model might be prone to quantum instabilities or spontaneous decay. Smoother distributions might maintain themselves more readily. The Notario drive also apparently reduces some secondary effects like Hawking radiation that could occur at the warp bubble boundaries. Energy requirements in the Notario model remain comparable to optimized Alcubierre drives, but the engineering challenges differ. You need to create gentler but more spatially extended warping of spacetime. This might actually be easier to achieve using Casimir-like effects or electromagnetic field manipulation, because you are not demanding extreme energy concentrations at specific points. The downside? The mathematics describing Notario drives gets even more complex than Alcubierre's already challenging equations. The field tensors involved require advanced differential geometry to fully understand. Most popularizations of warp drives focus on Alcubierre's model simply because it is easier to explain and visualize. Some researchers suggest the ideal solution might combine elements from both models. Use Notario's smooth boundary geometry to improve stability while incorporating Alcubierre's oscillating bubble walls to minimize energy requirements. Hybrid designs could potentially offer benefits from both approaches. Another team at the University of Göttingen in Germany explored whether topologically different warp geometries might work better. Instead of bubbles or toroids, what about helical warp fields or braided spacetime structures? The possibilities explode once you start treating spacetime as a malleable medium that can be shaped in creative ways. These geometric explorations remain purely theoretical for now. No one has built even a centimeter-scale Notario drive to test whether the mathematics translates to physical reality, but the diversity of proposed models suggests warp drive physics is maturing from a single wild idea into a genuine field of study with multiple competing approaches. That diversity is healthy. Different geometries might prove optimal for different purposes. Short-range warp jumps might use one configuration, while long-distance interstellar voyages use another. Just as aircraft come in many shapes depending on their mission, warp drives might eventually come in varied forms. The next question researchers started asking was whether anyone else in the universe might have already figured this out. And if so, could we detect the evidence they left behind? Gravitational waves ripple through space-time when massive objects accelerate violently. Colliding black holes, merging neutron stars, and supernovae all broadcast these ripples across the cosmos at light speed. We can now detect them using observatories like LIGO and Virgo, which measure space-time distortions smaller than a proton's diameter. In 2024, a research team at Germany's University of Potsdam had a clever idea. If warp drives warp space-time, they should also generate gravitational waves. The pattern would be distinctive, different from natural astronomical sources. A moving warp bubble would create a specific signature in the gravitational wave spectrum based on its geometry and speed. The researchers ran simulations showing exactly what these warp drive signatures would look like in gravitational wave detectors. They calculated the frequencies, amplitudes, and polarization patterns that different warp drive designs would produce. Then they started examining existing gravitational wave data, searching for matches. Nothing turned up in current archives. But gravitational wave astronomy is still young. LIGO only achieved its first detection in 2015. We have barely begun listening to the universe in this new way. Advanced detectors coming online in the next decade will be far more sensitive, capable of hearing fainter signals and distinguishing more complex patterns. If any advanced civilization within a few billion light-years has developed warp-drive technology, we might detect their ships moving through space by the gravitational ripples they leave behind. Those ripples would propagate outward at light speed, creating expanding shells of distorted space-time that eventually wash over Earth. The implications are staggering. We could discover faster-than-light travel is real not by inventing it ourselves, but by detecting alien civilizations already using it. Each detection would provide clues about how they built their warp drives, the energy signatures, the bubble geometries, the propulsion methods. It would be like finding alien footprints and reverse engineering their shoes. Some critics argue that civilizations advanced enough to build warp drives would probably be careful about detection. Maybe they shield their gravitational signatures or use modified warp geometries that minimize detectable emissions. Perhaps they avoid traveling through populated regions of the galaxy at warp speed to prevent accidentally revealing themselves. But even careful civilizations might leave occasional traces. A single unshielded warp jump, an emergency maneuver, or simply an old primitive warp drive from their early development could produce detectable signals. We only need to observe one clear example to prove the concept works in physical reality. The search expands beyond just gravitational waves. Warp bubbles moving at extreme speeds through interstellar gas and dust should create shock waves and radiation signatures. High-energy particles accelerating at the bubble boundary might produce gamma rays or cosmic ray bursts. Optical telescopes could search for the characteristic red and blue shifting of light around moving warp fields. No confirmed detections yet. The universe appears quiet on these frequencies, at least in the data we have examined so far. But absence of evidence is not evidence of absence, especially when we have only been listening seriously for a few years using limited sensitivity equipment. Imagine the moment we detect that first unambiguous warp drive signature. It would instantly answer two profound questions. Are we alone? And can faster-than-light travel really work? The discovery would revolutionize physics and potentially accelerate our own warp drive research by decades. We would know for certain the universe permits this technology. Until then, the search continues. More detectors come online every year. Algorithms improve. Analysis techniques become more sophisticated. If alien warp drives are out there, leaving their signatures on space-time itself, we will find them eventually. But what happens after? Reverse engineering alien technology sounds like science fiction, until you remember humans have done it throughout history. When Europeans first encountered gunpowder from China, they did not need to understand the full chemistry immediately. They could analyze the mixture, experiment with ratios, and eventually reproduce it. The same happened with countless technologies, from steelmaking to semiconductors. If we detect gravitational wave signatures from alien warp drives, we get an enormous advantage: direct observations of working models. The wave patterns would reveal bubble geometry, energy distributions, propulsion timing, and acceleration profiles. We could measure everything from the outside, even though we cannot see inside the technology itself. Advanced computer simulations could then model what configurations would produce those exact signatures. It becomes a massive inverse problem. Given the output, calculate the input. Engineers use this approach constantly to deduce internal structures from external measurements. Medical CT scans work the same way, reconstructing three-dimensional anatomy from two-dimensional X-ray projections. The German team's work laid groundwork for this approach. They created a library of simulated warp signatures, so when real detections occur, algorithms can rapidly match patterns to theoretical models. Think of it like facial recognition for warp drives. The system learns what different designs should look like, then identifies them in observational data. Some researchers worry about treaty violations or galactic etiquette. If advanced civilizations are hiding their warp signatures deliberately, should we respect that privacy? Others argue knowledge itself is not theft. We would not be stealing ships or attacking anyone. We would simply be learning from observations anyone could theoretically make. The technological gap might be enormous. An alien civilization using warp drives could be thousands or millions of years more advanced. Their fundamental physics understanding might include principles we have not discovered yet. Reverse engineering their technology could prove impossible if it relies on science beyond our current comprehension. But maybe not. Warp drives likely obey the same physics everywhere in the universe. General relativity works the same on alien worlds. If they found a way to generate negative energy density or manipulate space-time curvature, those mechanisms should be comprehensible to us once we observe the evidence. The math might be complex, but probably not incomprehensible. Historical precedent offers hope. When ancient Greeks discovered the Antikythera mechanism, an impossibly advanced astronomical calculator from 150 BC, they could not immediately understand it. But modern analysis eventually revealed its functions and clever engineering. Knowledge compounds. Each hint accelerates further discovery. Detecting even one confirmed alien warp signature would prove the technology works in physical reality under actual operating conditions. That confirmation alone would be invaluable. It would eliminate debates about whether various theoretical objections truly matter. The universe would have provided an existence proof. Funding for warp drive research would skyrocket overnight. Governments and private companies would race to develop working prototypes. The scientist or organization that successfully reverse engineers alien warp technology would instantly become the most important entity on Earth. The geopolitical implications boggle the mind, but detection-based development carries risks too. What if the signatures reveal catastrophically dangerous side effects? Maybe warp bubbles damage local space-time in ways that accumulate over time. Perhaps they create hazardous radiation or destabilize quantum fields. We might discover why alien civilizations use warp drives sparingly or avoid certain regions. Still, the potential rewards dwarf the risks. Learning faster than light travel from alien examples could save humanity centuries of dangerous experimentation. We could skip the trial and error phase and jump straight to proven designs. Of course, that assumes aliens exist, use warp drives, and do so in ways we can detect, which brings up the real nightmare. What if they are already here, watching us struggle with these calculations? Faster than light travel terrifies some physicists because it might allow time travel, and time travel creates logical impossibilities that threaten the consistency of reality itself. The grandfather paradox illustrates this perfectly. If you travel back in time and prevent your grandfather from meeting your grandmother, you never get born. But if you were never born, you never traveled back in time. But then your grandfather does meet your grandmother, so you do get born, so you do travel back, creating an infinite loop with no consistent resolution. Warp drives potentially enable similar paradoxes on cosmic scales. If you travel faster than light between two reference frames moving relative to each other, you could theoretically arrive before you left according to certain observers. The math gets ugly fast, involving closed time-like curves and violations of causality, but the conclusion seems inescapable. Faster than light movement and time travel are connected in relativity. Some physicists argue this connection proves faster than light travel must be impossible. The universe cannot permit causality violations because they create logical contradictions. If effects can precede causes, then nothing makes sense. You could receive answers before asking questions, die before being born, or prevent events that already happened. Reality would collapse into incoherence. Stephen Hawking proposed a chronology protection conjecture, suggesting unknown physics prevents time travel, even if equations appear to allow it. Whenever someone tries to create a time machine or travel faster than light, quantum effects or other mechanisms would intervene to prevent paradoxes. The universe protects its own consistency. Other scientists point out that warp drives might naturally avoid paradoxes through their specific geometry. The space inside the bubble moves faster than light relative to outside space, but nothing crosses the light speed barrier locally. Information cannot propagate backward in time through the bubble because the bubble isolates its interior from external reference frames. Imagine sending a signal from inside a warp bubble to outside. The signal would need to cross the bubble boundary, which separates two drastically different spacetime regions. That crossing might enforce causality by preventing any signal transmission that would create paradoxes. The bubble acts as an isolation barrier, preventing problematic information flow. Additionally, warp drives require continuous energy input to maintain the space-time distortion. That energy must come from somewhere, usually fusion or antimatter reactions happening in real time. You cannot retroactively provide energy to a warp bubble that already collapsed. This temporal directionality might inherently prevent backward time travel, even if you move faster than light. Some theoretical models suggest multiple timelines or parallel universes could resolve paradoxes. When you travel back and change the past, you create a new timeline branching from that moment. Your original timeline remains unchanged. You just cannot return to it. This many-worlds interpretation eliminates logical contradictions at the cost of introducing infinite parallel realities. Quantum mechanics already implies something similar through measurement and entanglement. The universe might naturally split into parallel branches at every decision point, with warp travel simply making those branches accessible. You would not change your own past. You would visit parallel versions where events unfolded differently. None of this is confirmed, though. We are speculating about hypothetical technologies that do not exist yet, using incomplete theories to predict their behavior. The honest answer is, we do not know whether faster-than-light travel creates paradoxes because we have never achieved it. The universe might have protection mechanisms we have not imagined. What remains certain is that building a working warp drive would immediately illuminate these questions. Either paradoxes emerge and we learn new physics explaining them, or they do not emerge and we learn causality protection is built into space-time. Either outcome represents a revolutionary discovery. The fear of paradoxes should not halt research. Scientists have ethical obligations to proceed carefully, but also to pursue knowledge about what reality permits. If warp drives ultimately prove impossible due to causality protection, that itself would be a profound insight into the structure of the cosmos. Time dilation at high velocities creates one of the cruelest aspects of near-light speed travel using conventional propulsion. Einstein's equations predict that time flows slower for rapidly moving objects compared to stationary observers. The faster you go, the more pronounced the effect becomes. At 99% of light speed, time passes 7 times slower for you than for people on Earth. This means a 10-year journey from your perspective equals 70 years back home. You return barely aged to find your friends and family elderly or dead, your children now older than you, society transformed beyond recognition. The isolation is profound and irreversible. You become unstuck in time, living a paradoxical existence where personal and external clocks no longer synchronize. The twin paradox demonstrates this dramatically. Identical twins separate, one traveling at high speed, while the other remains on Earth. When the traveling twin returns, they are younger. Their biological age, measured in heartbeats and cellular divisions, genuinely differs from their sibling. This is not an illusion or trick of perception. Time actually flows at different rates. Particle accelerators confirm this constantly. Unstable particles that should decay in microseconds last measurably longer when accelerated to 99% of light speed. Their internal clocks slow down. The universe does not care that this seems bizarre. The math works, the predictions match observations, and reality enforces these rules ruthlessly. For any interstellar mission using conventional propulsion, this temporal disconnect becomes unavoidable. A journey to a star 50 light-years away might take 100 years by Earth clocks, even at very high speeds. Travelers experience less time, perhaps 20 years if moving fast enough, but everyone they knew on Earth still ages the full century. Generation ships avoid this problem by accepting it. Multiple generations live and die during the voyage, so time dilation becomes irrelevant, but that creates different nightmares. Maintaining social stability for centuries, preserving mission focus across generations who never chose this fate, preventing technological and cultural drift that might make returning to Earth impossible. Warp drives elegantly sidestep this entire horror, because the ship inside a warp bubble is not actually moving through space at relativistic speeds. Time dilation does not apply. The bubble moves, carrying normal space-time with it. Inside, time flows at exactly the same rate as on Earth. You could travel to Proxima Centauri in weeks, return home, and find only weeks have passed everywhere. This represents one of warp drive's biggest advantages beyond simple speed. You maintain temporal connection with home. You can leave for years, knowing you will return to the same era. Your relationships remain intact. Your knowledge stays relevant. You do not become a temporal refugee displaced from your own time. Crew members would experience normal time flow, aging naturally, during the journey. No suspended animation needed. No generational planning. No psychological trauma from temporal disconnect. The mission timeline would be measured in human lifetimes rather than civilizational epochs. This also makes warp travel economically viable. A corporation funding an interstellar mining operation needs results within investment horizons, measured in decades, not centuries. Governments planning colonization efforts cannot wait generations for feedback. Warp drives enable interstellar activity to operate on timescales that make sense for human institutions and motivations. The lack of time dilation also avoids causality problems. When time flows consistently everywhere, cause and effect maintain proper order. You cannot exploit relativistic time differences to create paradoxes or send information backward through time by clever routing between reference frames. Of course, this all assumes warp bubbles work as theorized. If they have unexpected side effects on temporal flow, all bets are off. But according to current models, warp travel appears to offer truly fast transportation without the temporal baggage that makes relativistic travel so psychologically and socially problematic. Escaping time dilation alone makes warp drives worth pursuing, even if speeds only matched conventional propulsion. But there is another nightmare that warp drives avoid, one even more immediately lethal. Accelerating a human body to extreme speeds using conventional propulsion would kill you long before reaching relativistic velocities. The forces involved are simply too intense for biological tissue to survive. Astronauts experience about 3 times Earth's gravity during rocket launches, pressed into their seats with triple their normal weight. Fighter pilots can briefly withstand up to 9 times Earth's gravity during extreme maneuvers before losing consciousness. Reaching even 1% of light speed in a reasonable time frame requires sustained acceleration thousands of times stronger than Earth's gravity. Your body would not just feel heavy, it would disintegrate. Bones would shatter under compression, blood vessels would rupture, your brain would be crushed against the inside of your skull. Death would be instant and total. Some science fiction proposes using acceleration couches filled with liquid to support the body evenly, reducing stress on any single point. This helps at moderate acceleration but fails completely at extreme forces. You cannot distribute enough pressure evenly enough to prevent liquefaction of tissues when acceleration reaches hundreds or thousands of Earth gravities. Generation ships avoid this by accelerating extremely slowly over decades. Your body never experiences dangerous forces because thrust is spread across years of gentle acceleration. This works, but demands centuries of travel time. You are trading lethal acceleration for glacial speed. Suspended animation might help, but freezing humans causes ice crystal formation that shreds cells. Cryogenic preservation remains science fiction despite decades of research. Even if achieved, thawing someone after high acceleration travel might just give you a thoroughly scrambled corpse. The meat grinder problem represents a fundamental barrier to fast conventional interstellar travel. You cannot accelerate human bodies quickly enough to reach significant fractions of light speed within a single lifetime. The physics is unforgiving. Biology has limits that technology cannot eliminate. Warp drives solve this completely and elegantly. The spacecraft inside the bubble does not accelerate at all. Zero g-forces. You experience no inertial effects whatsoever because you are not actually moving. Space moves around you while you remain stationary. Your coffee does not slosh, your stomach does not drop, your body experiences no stress. This is not magic, it is geometry. Inside the bubble, local space-time remains completely flat and normal. The extreme curvature exists only at the bubble boundary. You live in an island of calm reality while the cosmos reorganizes itself around you. Acceleration happens to space, not to your ship. You could theoretically go from stationary to 10 times light speed instantaneously with zero physical sensation. The transition would be imperceptible to anyone inside the bubble. No crushing forces, no gradual build-up, just instant velocity change without any of the normally associated effects. Reality inside stays constant, while your relationship to outside reality transforms. This makes warp travel not just fast but comfortable and safe from an acceleration perspective. Fragile equipment would not need special mounting. Delicate experiments could run during transit. Passengers could walk around, eat meals, and go about normal activities while traveling faster than light. The journey becomes routine rather than an endurance test. The implications extend beyond comfort. You could transport anything regardless of fragility. Living organisms, complex machinery, volatile chemicals, anything that exists can be moved without special preparation or hardening against acceleration forces. This opens possibilities for interstellar colonization that would be impossible with conventional propulsion. Imagine transporting an entire ecosystem to a new world. Plants, animals, microorganisms, all traveling together in a self-sustaining environment. With conventional propulsion, keeping such a system alive during decades of travel with violent acceleration phases seems nearly impossible. With warp drives, it becomes straightforward. Just maintain life support during what amounts to a brief, smooth trip. These advantages stack on top of each other. Warp drives offer speed without time dilation, movement without acceleration forces, and travel without requiring exotic life support or suspended animation. Every problem that makes conventional interstellar travel nearly impossible simply vanishes inside a warp bubble. But none of this matters if we cannot actually build one. The interior of a warp bubble would feel absolutely ordinary. You could not tell whether the bubble was moving at 10 times light speed or sitting completely still. Physics inside operates exactly like physics on Earth because the space-time inside remains flat and undistorted. The extreme warping happens only at the boundary, creating a protective shell around normal reality. Your watch would tick at the same rate as watches back on Earth. Your cells would age normally. Chemical reactions would proceed at standard speeds. Light would travel at its usual velocity relative to the bubble interior. Nothing about the fundamental constants of physics would change. You exist in a pocket of normal spacetime that happens to be moving through the larger universe. This isolation from external reference frames creates interesting communication challenges. Radio signals from inside the bubble, trying to reach outside, would need to cross the boundary where spacetime curves dramatically. That transition might block electromagnetic radiation entirely, making the bubble opaque to conventional communications. You would essentially be cut off during transit, unable to send or receive messages until dropping out of warp. This could last days or weeks, depending on distance traveled. Mission planners would need to account for these blackout periods, ensuring ships carry complete information and decision-making authority rather than relying on real-time guidance from home. Looking out windows would present bizarre visuals. Light from stars ahead would be massively blue-shifted, compressed into gamma rays by the space-time contraction in front of the bubble. Stars behind would redshift into radio waves, stretched by spatial expansion. The visible spectrum would narrow to a ring around your direction of travel, possibly showing distorted, smeared views of the cosmos. Some models suggest you might see nothing at all through forward-facing windows. The compressed space ahead could create an event horizon-like effect where light cannot escape the warp field to reach your eyes. You might fly blind, navigating by instruments rather than direct observation. Temperature inside would remain stable. The bubble boundary shields you from external conditions, including the cosmic microwave background radiation, interstellar dust impacts, and any other environmental hazards. You could theoretically warp through a supernova without experiencing its heat or radiation inside your protected bubble. The gravity inside would match whatever artificial gravity systems you installed, or be zero if you have none. The warp field itself does not create internal gravitational effects because space-time inside remains flat. This differs dramatically from natural gravitational fields, where space-time curvature causes observable effects throughout the region. Energy systems powering the warpdrive would operate normally from the ship's perspective. Fusion reactors, antimatter containment, power distribution networks all function exactly as designed. The exotic physics requirements exist only at the boundary where space-time transitions from normal to warped states. Crew psychology might be the biggest challenge. Being isolated in a bubble of normal physics while the universe restructures around you could feel profoundly unnerving. Some astronauts might experience existential anxiety from knowing they exist in a tiny pocket of reality insulated from the larger cosmos. Others might find it comforting, a safe haven in the vast strangeness of space. Training would emphasize maintaining routines and psychological stability during what amounts to sensory deprivation from the external universe. The journey might be brief in duration, but the experience of being fundamentally disconnected from normal space-time could challenge mental health in unexpected ways. Still, compared to spending decades in a conventional spacecraft, slowly crawling between stars, while aging differently than everyone you know, a few weeks in a comfortable warp bubble seems vastly preferable. The psychological challenges are manageable. The physics advantages are revolutionary, if we can build it. Which brings us to who might already be trying. NASA's Advanced Propulsion Physics Laboratory operated quietly for years under Harold White's direction, tucked away in Building 9 at Johnson Space Center in Houston. The official missions sounded mundane: study exotic propulsion concepts for potential future applications. The unofficial reality involved active warp drive research, funded through carefully worded budget requests. White's team built specialized equipment to measure nanoscale space-time distortions. They experimented with different capacitor configurations, trying to amplify Casimir effects. They ran simulations exploring optimal warp bubble geometries. The work proceeded carefully, methodically, always with plausible scientific cover stories for anyone asking uncomfortable questions. Then came the 2021 announcement about detecting warp bubble signatures in the lab. Suddenly, the work was not so quiet anymore. Media coverage forced NASA to either disavow the research or acknowledge its legitimacy. They chose a middle path, confirming the research exists while emphasizing its extremely preliminary nature and decades-long timeline to potential applications. Behind closed doors, funding reportedly increased. More physicists joined the team. Equipment orders expanded. The lab that barely existed officially now had multiple research tracks running simultaneously. One focused on understanding the Casimir effect better. Another explored metamaterials that might manipulate vacuum energy. A third investigated whether quantum entanglement could play a role in space-time warping. Other NASA centers got involved. Glenn Research Center in Ohio has propulsion expertise. Jet Propulsion Laboratory in California brings advanced engineering capabilities. Ames Research Center contributes computational modeling resources. The research network quietly expanded across multiple facilities, each working on different pieces of the larger puzzle. Government classification adds murky layers. Some warp drive research likely proceeds behind security clearances, invisible to public oversight. If breakthrough discoveries occur in classified programs, we might not learn about them for years or decades. Military applications of faster-than-light travel are obvious enough that defense agencies certainly fund their own parallel research. The Department of Energy probably participates, given the extreme energy requirements involved. Their national laboratories have expertise in plasma physics, fusion reactions, and high-energy particle interactions. If exotic matter generation proves possible, DOE facilities would be best positioned to attempt it. International collaboration remains limited by security concerns. NASA shares some basic research results with allied space agencies, but anything approaching practical applications gets locked down. No one wants to hand potential adversaries a massive technological advantage. The first nation to achieve working warp drive would dominate both space exploration and potentially warfare. This creates an unfortunate secrecy around research that humanity as a whole might benefit from sharing. Scientists at institutions worldwide probably duplicate efforts, each struggling with similar problems that collaborative work could solve faster. But geopolitical realities prevent open cooperation on anything militarily sensitive. Insiders occasionally leak hints. Conference presentations mention unexplained anomalies in propulsion experiments. Patent applications describe exotic space-time manipulation techniques using vague language. Researchers give talks that carefully dance around classified details while signaling that more is happening than public statements admit. How close is NASA really to a working prototype? Publicly, they maintain that practical warp drives remain far future speculation, possibly achievable in 50 to 100 years with sustained research. Privately, some researchers suggest breakthroughs could come much sooner if critical problems get solved. The gap between those timelines might hide classified progress, or simply reflect the difference between conservative official estimates and optimistic scientific hope. What seems certain is that serious, well-funded research continues at multiple government facilities using increasingly sophisticated equipment and techniques. Warp drives transitioned from science fiction to legitimate government-funded physics research. That represents enormous progress regardless of how far from practical applications we currently stand. But government labs are not the only ones chasing this dream anymore. Elon Musk rarely discusses warp drives publicly, but SpaceX's long-term plans for Mars colonization and beyond suggest someone there is thinking about faster propulsion. The company's Starship program aims to establish self-sustaining Mars cities, but Mars is just a stepping stone in Musk's vision. He has repeatedly stated that making humanity a multiplanetary species requires reaching other star systems, eventually. SpaceX employs some of the world's best propulsion engineers and theoretical physicists. Their facilities in Hawthorne, Boca Chica, and Cape Canaveral house advanced laboratories capable of cutting-edge research. The company's culture encourages moonshot thinking and rapid prototyping. If any private organization would seriously pursue warp drive research, SpaceX tops the list. Specific details remain scarce. SpaceX treats proprietary research like classified information, revealing only what benefits them strategically, but job postings occasionally hint at exotic propulsion studies. Engineers with backgrounds in plasma physics, quantum field theory, and general relativity get hired for unspecified advanced projects. Equipment purchases include specialized sensors and high-energy systems with no obvious connection to conventional rocket development. Rumors circulate about secret test facilities in remote locations where unusual experiments occur away from public scrutiny. Some former employees describe research tracks exploring physics beyond chemical rockets, though non-disclosure agreements prevent specifics. One anonymous source mentioned studying space-time manipulation techniques, but verification proved impossible. Musk's other companies might contribute. Boring Company expertise in underground construction could build shielded facilities for dangerous high-energy experiments. Tesla's battery and power management technology might enable the precise energy control needed for warp field generation. Neuralink's work on brain-computer interfaces could help manage the complex calculations required for real-time warp field manipulation. The financial resources available to Musk personally and through his companies dwarf most government research budgets. SpaceX generates billions from Starlink satellite launches and NASA contracts. That revenue could easily fund speculative physics research if Musk decided the potential payoff justified the investment. He has repeatedly demonstrated willingness to bet on long-shot technologies that others dismiss as impossible. Blue Origin, Jeff Bezos' space company, presumably conducts similar research. Bezos shares Musk's long-term vision of expanded human presence in space. Blue Origin employs talented engineers and physicists with access to substantial resources. Their New Glenn rocket and lunar lander programs generate revenue, while more speculative work proceeds quietly in the background. Other aerospace companies, like Lockheed Martin, Boeing, and Northrop Grumman, maintain advanced concepts, divisions that explore exotic propulsion. These operate with less publicity than SpaceX, but likely pursue similar research directions. Defense contracting relationships give them access to classified research and government funding for speculative projects. Silicon Valley billionaires fascinated by space might fund independent research groups. Yuri Milner's breakthrough initiatives already sponsors projects searching for alien life and developing interstellar probes. Breakthrough Starshot aims to send tiny, laser-propelled craft to Alpha Centauri at 20% light speed. These initiatives demonstrate willingness to fund revolutionary propulsion concepts. Private research avoids some government bureaucracy and classification restrictions, enabling faster iteration and more risk-taking. But it also lacks the institutional knowledge, facilities, and collaborative networks that government laboratories provide. The ideal situation might involve partnership between public and private sectors, but intellectual property concerns and security classifications complicate such arrangements. What remains clear is that multiple well-funded organizations beyond NASA are pursuing faster-than-light propulsion research. The race is on, though conducted mostly in secrecy. Whoever achieves the first breakthrough will either become incomprehensibly wealthy and powerful, or spark a new era of space exploration that transforms humanity. Possibly both. The real question is which of the three leading warp drive approaches will succeed first. Three distinct warp drive concepts have emerged as the most promising candidates for actual development. Each takes a different approach to the same fundamental problem. How do you warp spacetime in ways that enable faster-than-light travel without requiring impossible materials or infinite energy? The Alcubierre drive remains the most famous. It creates a bubble where space contracts ahead and expands behind, generating a wave that carries the ship forward. Recent optimizations by Harold White and others have reduced energy requirements dramatically. The challenge lies in generating sustained exotic matter or negative energy density effects at scales large enough to encompass a spacecraft. Current research focuses on whether cascading Casimir effects could be amplified through resonance phenomena. If you could create standing waves of negative energy density that reinforce each other, the total effect might reach useful scales, even though individual Casimir forces remain tiny. Think of it like how opera singers can shatter wine glasses through acoustic resonance, amplifying small vibrations into destructive forces. The Natario drive offers improved stability through smoother spacetime distortions. Instead of sharp boundaries requiring intense energy concentrations, it distributes warping across larger volumes. This might be achievable using carefully shaped electromagnetic fields or plasma configurations that create the right energy density gradients without requiring exotic matter at all. Researchers at several universities are exploring whether toroidal plasma containment systems, like miniature fusion reactors, could generate Natario-style warp fields as a side effect. The plasma itself would provide the energy density variations needed to curve spacetime, though controlling it precisely enough remains extremely difficult. A third approach, less publicized but potentially revolutionary, involves exploiting dark energy directly. Dark energy constitutes 70% of the universe's total energy density and exhibits negative pressure properties, similar to what warp drives require. If we could locally concentrate or manipulate dark energy, we might generate warp effects without needing exotic matter or Casimir amplification. The catch? We barely understand what dark energy is, let alone how to manipulate it. Current physics cannot explain dark energy's origin or predict its behavior beyond observing its effects on cosmic expansion. Learning to control it would require breakthrough discoveries in fundamental physics. But the potential payoff is enormous. An infinite energy source with exotic properties already permeating all of space could provide the fuel warp drives need. Some researchers propose hybrid approaches combining elements from all three concepts. Use Alcubierre-style oscillating bubble geometry for energy efficiency, Nasaresearch-style smooth boundaries for stability, and dark energy manipulation for fuel. The optimal solution might require blending insights from multiple models rather than rigidly following any single approach. Computer simulations test these concepts constantly, exploring parameter spaces to find combinations that might work. Supercomputers run millions of iterations, trying different bubble shapes, energy distributions, and field configurations. The search resembles drug discovery, where researchers test countless molecular variants hoping to find one that produces desired effects. Laboratory experiments lag behind simulations because building equipment to test warp field generation remains extraordinarily difficult. Measuring nanoscale space-time distortions requires instruments at the edge of current technological capabilities. Scaling up to even millimeter-scale effects would need entirely new apparatus that does not exist yet. Progress happens incrementally. Each laboratory success, even tiny ones, validates pieces of the theory and suggests paths forward. Each simulation identifies parameter ranges worth exploring or dead ends to avoid. The field slowly advances from pure speculation toward engineering reality. No one knows which approach will succeed first, or whether some completely different concept will unexpectedly work better. The race between competing designs drives innovation as research groups pursue different strategies, hoping theirs proves optimal. This competitive diversity increases the chances that someone, somewhere, will find a configuration that actually functions. But all these approaches face the same underlying challenge. Manipulating the structure of space-time itself requires understanding physics at a deeper level than we currently possess. Classical physics described the universe as clockwork. Particles had definite positions and velocities. Forces acted predictably according to clear mathematical laws. Everything was, in principle, calculable and deterministic. If you knew the initial conditions perfectly, you could predict the future with complete accuracy. This worldview dominated science for centuries. Quantum mechanics shattered that comfortable certainty. At microscopic scales, particles exist in fuzzy probability clouds rather than precise locations. They behave like waves and particles simultaneously. Measuring one property makes other properties fundamentally uncertain. The universe operates on probability and randomness rather than clockwork precision. Even stranger, quantum mechanics revealed that empty space is not empty. Virtual particles constantly pop into and out of existence everywhere, borrowing energy from quantum uncertainty and paying it back before the universe notices. This churning quantum foam underlies all of reality, creating effects we can measure even though the particles themselves remain invisible. The Casimir effect proves this directly. Those metal plates attracting each other in apparent defiance of classical physics are being pushed together by imbalances in quantum vacuum fluctuations. The universe's microscopic reality does not follow the intuitive rules that govern our everyday experience. Weirdness is fundamental, not exceptional. Warp drives exploit this quantum weirdness. They rely on manipulating quantum vacuum energy to create regions of negative energy density. This requires understanding and controlling quantum phenomena at scales and intensities far beyond current capabilities. We need to make quantum effects macroscopic and sustained rather than microscopic and transient. Quantum field theory provides the mathematical framework, but applying it to practical engineering remains largely aspirational. The calculations become impossibly complex when dealing with curved spacetime and strong gravitational fields. Physicists can write the equations but cannot solve them for realistic scenarios. Supercomputers help but still fall short of modeling full warp drive dynamics quantum mechanically. This gap between theory and practice represents one of the biggest obstacles to warp drive development. We know quantum effects must be involved. We understand some relevant principles, but we lack the computational tools and physical intuition to design systems that actually work. It resembles trying to build computers in the 1800s. The basic physics is there, but the engineering knowledge remains centuries away. Recent developments in quantum computing might help. Quantum computers exploit the same weird properties that make quantum mechanics so counterintuitive. They could potentially simulate quantum vacuum effects and space-time curvature more efficiently than classical computers. If quantum computers can model warp field dynamics accurately, they might identify configurations that classical analysis misses. Quantum entanglement adds another intriguing possibility. Entangled particles influence each other instantaneously across any distance, apparently violating the speed of light limit. Einstein called this spooky action at a distance and found it deeply troubling. Modern experiments confirm it happens, though careful analysis shows no information actually travels faster than light through entanglement. Could entanglement play a role in warp drives? Some speculative theories suggest entangled quantum states, spanning the warp bubble boundary, might enable information transfer between inside and outside despite the space-time distortion. Others propose using entanglement to coordinate quantum vacuum manipulations across large volumes, creating coherent warp fields. These ideas remain highly speculative, bordering on science fiction. But quantum mechanics has repeatedly proven that reality operates on stranger principles than common sense suggests. Dismissing ideas just because they sound impossible has historically been a mistake when dealing with quantum phenomena. The transition from classical to quantum thinking represents a philosophical shift as much as a scientific one. We must accept that the universe fundamentally operates according to probabilistic rules we cannot visualize intuitively. Warp drives force us deeper into this quantum realm, where ghost particles and uncertain properties somehow conspire to create macroscopic effects. Learning to engineer quantum phenomena with the same confidence we engineer classical mechanics could take decades or centuries. But the potential rewards include not just warp drives, but entirely new technologies based on manipulating reality's quantum substrate. We stand at the threshold of a new physics era, and the key might already exist, hidden in the darkest parts of the universe. Dark energy remains one of physics' deepest mysteries. Observations show the universe's expansion is accelerating, driven by some unknown energy that permeates all of space. This dark energy comprises 70% of everything that exists, yet we cannot detect it directly, do not know what it is, and have only the vaguest ideas about its properties. What we do know is intriguing. Dark energy exhibits negative pressure, pushing space apart rather than pulling it together like normal matter and energy. This negative pressure property resembles exactly what warp drives need to function. If dark energy could be locally concentrated or manipulated, it might provide the exotic fuel that makes warp bubbles possible without requiring impossible materials. The idea sounds like magic, but consider this. Dark energy already exists everywhere. You are swimming in it right now. Every cubic meter of empty space contains a small amount of dark energy. The universe has thoughtfully provided an infinite fuel source with precisely the exotic properties warp drives require. We just need to learn how to mine it. Current physics cannot explain where dark energy comes from or what gives it negative pressure. Leading theories suggest it might be a property of space-time itself, a cosmological constant that represents vacuum energy density. Other ideas propose it is a dynamic quantum field slowly evolving over cosmic time. Nobody knows for certain. This ignorance makes manipulation seem impossibly distant. How do you control something you do not understand? Yet history shows humans often harnessed phenomena before fully understanding them. Ancient people used fire for millennia before learning about oxidation chemistry. Farmers bred crops for 10,000 years before discovering genetics. Practical application can precede complete theoretical understanding. What if warp bubble generation accidentally taps into dark energy? The space-time distortions created by warp fields might naturally draw on the dark energy permeating that region. The bubble could be fueled by the same mysterious force accelerating the universe's expansion. This would elegantly solve the exotic matter problem by using energy that already exists rather than generating it artificially. Some theoretical models explore whether warp bubbles create regions where dark energy concentrates or behaves differently. The intense space-time curvature at bubble boundaries might alter how dark energy manifests locally. If you could create conditions where dark energy temporarily exhibits even stronger negative pressure, that amplification might generate the warp effect. Quantum vacuum energy, which powers the Casimir effect, might actually be related to dark energy. Both involve energy densities in apparently empty space. Both exhibit properties that classical physics did not predict. Understanding one might illuminate the other. If Casimir-style vacuum manipulation can scale up to useful sizes, we might simultaneously be learning to manipulate dark energy. The biggest challenge is detection. We know dark energy exists because we measure its effects on cosmic expansion, but detecting it locally is impossible with current instruments. It is like trying to measure tiny currents while standing in the ocean. The local fluctuations are swamped by cosmic-scale averages. Developing sensors capable of measuring dark energy density variations in laboratory settings remains a massive technical hurdle. Some researchers propose looking for dark energy signatures in gravitational wave data. Just as warp bubbles should create distinctive gravitational waves, dark energy fluctuations might produce their own patterns. Advanced detectors coming online over the next decade might achieve the sensitivity needed to measure these effects. If we could map dark energy distributions precisely, we might discover natural concentrations or voids that reveal manipulation techniques. Perhaps regions near black holes or neutron stars exhibit unusual dark energy behavior worth studying. The universe might have already demonstrated dark energy manipulation in extreme environments. This research direction remains highly speculative, but the potential payoff justifies investigation. Dark energy represents an enormous untapped resource if we could learn to access it. For warp drive specifically, it could transform an impossible engineering challenge into a merely extremely difficult one. The universe might have provided the fuel we need. We just have to figure out how to fill the tank. Einstein taught us to think of space-time as a smooth, continuous fabric stretching across the cosmos. Massive objects create dents in this fabric. Accelerating masses create ripples that propagate as gravitational waves. It is an elegant picture that has guided physics for over a century. But what if space-time is not actually smooth? What if it has seams, boundaries, or discontinuities where the rules change? Quantum mechanics suggests space-time might be grainy at the smallest scales. The Planck length, about 10 to the minus 35 meters, represents the smallest meaningful distance in physics. Below that scale, quantum fluctuations make the very concept of smooth space-time break down. Space-time might be pixelated like a computer screen, appearing smooth only when viewed from far away. These quantum grains of space-time could represent seams in the fabric, locations where manipulation might be easier or different effects occur. If warp drives require tearing or stitching space-time, finding natural seams where the fabric is already weakest makes sense. It resembles how tailors cut fabric along the weave rather than fighting against it. Black holes create the most dramatic space-time boundaries we know about. The event horizon marks a sharp transition where physics fundamentally changes. Inside, space and time swap roles. Escape becomes impossible. Time flows toward the singularity rather than toward the future. These boundaries might teach us about creating artificial space-time edges for warp bubbles. Hawking radiation emerges from quantum effects at the event horizon, where virtual particle pairs get split by intense gravity. One particle falls in while the other escapes, creating apparent radiation from the black hole. This demonstrates that extreme space-time curvature enables unusual quantum phenomena. Warp bubble boundaries might exploit similar effects. Wormholes, if they exist, represent ultimate space-time seams. They connect distant regions through a shortcut, a tunnel through the fabric itself. Theoretical models suggest wormholes require exotic matter to hold them open, the same stuff needed for warp drives. Perhaps warp bubbles are essentially mobile, self-contained mini wormholes carrying a pocket of normal space-time through the larger universe. String theory proposes that space-time has additional dimensions beyond the familiar 3+ time. These extra dimensions are curled up so tightly we cannot detect them directly. But at high energies or extreme curvatures, they might become accessible. Warp drives, operating at space-time boundaries, might tap into these hidden dimensions. Some physicists explore whether space-time has an underlying microstructure, like how water molecules create liquid properties. If space-time emerges from something more fundamental, understanding that substrate might reveal manipulation techniques. Loop quantum gravity and other approaches propose that space-time itself is woven from discrete quantum loops or networks. This perspective makes warp drives seem more plausible. If space-time has component parts, you might be able to take it apart and reassemble it differently. The fabric is not a single piece, but a weaving that can be unraveled and rewoven in patterns that create warp effects. This requires technology to manipulate space-time's fundamental building blocks, whatever those turn out to be. Cosmic strings, hypothetical defects in space-time left over from the early universe, would represent natural seams on cosmic scales. These one-dimensional objects with enormous mass density could stretch across galaxies. If they exist, and if we could find them, they might demonstrate how space-time defects behave and whether they could be artificially created. All of this remains highly theoretical. We do not know if space-time has seams, grains, or underlying structure. The smooth fabric picture might be completely accurate. But exploring alternatives opens new possibilities for warp drive physics. If space-time is more complex than Einstein imagined, it might also be more manipulable. The key is finding where reality's fabric is already weak or structured differently. Those locations might be natural laboratories for testing space-time manipulation, or sites where warp field generation becomes easier. The universe might have provided hints about how to reshape it if we look in the right places, which brings us to the most important question: how close are we really? Every breakthrough brings new timelines and predictions. Optimists claim working warp drive prototypes could appear within 10 to 15 years if research continues at current pace. Pessimists argue we are centuries away from practical applications. The truth likely falls somewhere between, but narrowing that gap requires understanding what specific problems remain unsolved. Energy generation represents the most immediate challenge. Even with optimized geometries and reduced requirements, warp drives need enormous power output controlled with extreme precision. Current fusion research progresses steadily, but has not achieved sustained net energy gain yet. Antimatter production remains painfully slow and expensive. Dark energy manipulation exists only in theoretical papers. Creating negative energy density at useful scales presents an even harder problem. White's team detected nanoscale warp geometry, but scaling up by a factor of 10 billion seems impossibly difficult. The Casimir effect weakens rapidly with distance. Amplification techniques remain purely speculative. Without breakthrough discoveries in quantum vacuum manipulation, this obstacle alone could delay practical warp drives for decades. Materials science faces extreme demands too. Any spacecraft surrounded by intense warp fields would experience stresses and radiation unlike anything current materials can withstand. The ship's structure must remain stable, while space-time warps violently just meters away. Designing materials that survive these conditions will require extensive testing that cannot begin until we can generate warp fields to test them against. Navigation and control systems need complete reinvention. How do you steer when you cannot see your destination? How do you avoid collisions while traveling faster than light? What happens if something goes wrong inside a warp bubble moving at 10 times light speed? These engineering challenges demand solutions before any crewed mission becomes remotely safe. Theoretical physics still has gaps that make predictions uncertain. We cannot fully simulate warp drive dynamics using current equations. Quantum effects at bubble boundaries remain poorly understood. Whether dark energy actually helps or creates new problems is unknown. Each of these uncertainties could hide show-stopping issues that only emerge during actual construction attempts. International cooperation would accelerate progress but remains unlikely given national security concerns. If breakthrough occurs at a classified facility, commercial applications might lag years or decades behind military ones. The first warp drive might be a secret military project that public science does not learn about until much later. Funding levels matter enormously. Current warp drive research operates on budgets measuring millions annually across all programs worldwide. Fusion research receives billions. The Manhattan Project spent $27 billion in today's money over 4 years. Apollo consumed $150 billion. If humanity committed those resources to warp drives, 10-year timelines might be achievable. Without that commitment, progress will crawl. Some researchers privately admit that a single critical breakthrough could change everything overnight. If someone discovers how to generate scalable negative energy density, or learns to manipulate dark energy, or finds some completely unexpected space-time manipulation technique, the entire timeline collapses. We could go from barely able to measure nanoscale effects to building test vehicles within a few years. History shows technological revolutions often happen faster than experts predict once key enabling discoveries occur. Powered flight went from barely possible to routine in 2 decades. Nuclear energy became practical within 5 years of theoretical understanding. Computers shrunk from room-sized to pocket-sized in 30 years. The right breakthrough triggers explosive progress. Conversely, some challenges prove harder than anticipated. Fusion power has been 30 years away for over 60 years. Quantum computing took decades longer than early optimists predicted. Some technological barriers persist stubbornly despite massive investment and brilliant minds attacking them. Which category does warp drive fall into? That depends on whether the universe actually permits the technologies we need. If reality allows negative energy generation at scale, efficient dark energy manipulation, and stable warp field maintenance, then it becomes an engineering race. If the universe has protections preventing these effects at useful scales, we might bang our heads against physics limits forever. The only way to find out is to keep pushing forward, fund the research, build better instruments, run more experiments, test wilder theories. Someone, somewhere, needs to find the key that unlocks the next level of physics. When that happens, the countdown truly begins. Faster than light travel represents more than just technical achievement. It fundamentally transforms what humanity can become. Every great migration in our history, from Africa to every continent, across oceans to new worlds, expanded our potential and forced us to adapt and innovate. The stars represent our next frontier, but only if we can reach them. With warp drives, the galaxy opens up. Hundreds of potentially habitable planets within 50 light-years become accessible destinations. We could establish colonies on worlds better suited to life than Mars ever will be. Humanity would spread across multiple star systems, ensuring our survival even if disaster strikes Earth. We evolve from a single-planet species facing existential risk to a multi-world civilization with redundancy and resilience. The economic implications stagger the imagination. Asteroid mining becomes trivial when you can warp to the asteroid belt and back in hours. Rare elements abundant in other solar systems could be harvested and returned. Energy resources available from stars or gas giants far exceed anything Earth provides. A spacefaring civilization with warp capability would command resources that make current global economy look minuscule. Scientific discovery would accelerate dramatically. Direct study of alien ecosystems, close observation of stellar phenomena, hands-on investigation of black holes and neutron stars all become possible. Questions about life's origins, planetary formation, and cosmic evolution could be answered through direct observation rather than distant speculation. Every new world visited would rewrite textbooks and challenge assumptions. Contact with alien civilizations becomes likely if they exist within our reach. Instead of waiting centuries for radio signals to cross space, we could physically visit nearby systems and search for life directly. We might find ruins of extinct civilizations, encounter primitive life, or make contact with intelligence equal or superior to ours. The implications for philosophy, religion, and human identity would be profound. Cultural transformation seems inevitable. A humanity spread across the stars would diversify in ways we can barely imagine. Isolated colonies would develop unique customs, languages, and societies adapted to their worlds. We might fragment into distinct branches of human civilization, or maintain unity through rapid warp-speed communication and travel. Either path leads to futures radically different from our current reality. The risks cannot be ignored. Warpdrive might enable terrifying weapons systems. Nations or groups with this technology would dominate those without. Space warfare could erupt on scales that make Earth's conflicts look trivial. We need frameworks for preventing militarization before the technology matures, though history suggests such efforts usually fail. Environmental consequences remain unknown. Does repeated warp travel damage space-time? Could we accidentally destabilize regions of space through overuse? Might warp bubbles leave behind pollution or side effects that accumulate dangerously? We need to study these questions before deploying the technology widely. Ethical debates will intensify. Who gets access to warp ships? How do we prevent exploitation of newly discovered worlds? If we find primitive life, do we have obligations not to interfere? What rights do future colonists have regarding independence from Earth? These questions have no easy answers, but demand consideration before crises force hasty decisions. The psychological impact might be most profound. Knowing we can reach the stars changes how humans think about our place in the cosmos. We stop being imprisoned on a fragile planet and become truly free to explore. The expansion of possibility space for human achievement and experience could inspire generations, just as the Apollo program inspired millions despite its limited practical benefits. This moment in history, right now as researchers inch toward functional warp-drive physics, might be looked back upon as the pivot point where humanity's future trajectory shifted permanently. Either we solve this challenge and become a stellar civilization, or we remain confined to our solar neighborhood perhaps forever. The choice is not really ours. We can fund research and push boundaries, but the universe decides whether the physics allows what we need. Reality might simply not permit warp drives, no matter how cleverly we try. Or it might have already provided everything necessary, waiting for us to figure out the combination that unlocks it. Either way, the attempt itself matters. Pushing against the boundaries of possible expands human knowledge and capability, even if we never achieve the primary goal. The technologies developed while pursuing warp drives will spin off applications benefiting humanity regardless. We learn by trying to do impossible things. The scientists working in laboratories today, measuring nanoscale distortions and running quantum simulations, are trailblazers exploring physics frontiers that might not pay off for decades. They work on timescales longer than careers, pursuing knowledge that may only benefit future generations. That kind of thinking built everything great our civilization has achieved. Someone reading this might be the person who solves it. Maybe you are the engineer who designs the first scalable negative energy generator, or the physicist who cracks dark energy manipulation. or the programmer who writes the code enabling real-time warp field control. The breakthrough could come from anywhere, from anyone with curiosity and determination. The universe is incomprehensibly vast. Light from the edge of the observable cosmos has been traveling toward us for over 13 billion years, and will never arrive because space expands faster than light can cross it. We exist in a tiny bubble of causally connected space, able to interact only with the limited region where light has had time to reach since the Big Bang. Warp drives would not change those cosmic limits. Even at 1,000 times light speed, the observable universe would take millions of years to cross. But they would transform what is practically achievable for human civilization operating on human timescales. The nearby galaxy, containing billions of worlds, would finally be accessible. That is the prize we are chasing. Not infinite reach or godlike power, but simply the ability to explore our cosmic neighborhood within lifetimes rather than millennia. We want to visit a few dozen nearby stars, investigate planets that telescopes show look promising, and establish humanity among the stars, while Earth remains our home. The race toward 10 times light speed is not just about science or engineering or national prestige. It is about whether humanity has a future among the stars, or remains forever confined to this single planet, watching the cosmos from a distance we can never cross. That future is being written in laboratories right now. The next chapter of human history is taking shape one equation, one experiment, one breakthrough at a time, and it might arrive sooner than any of us expect.